ready to begin if people are, if
right,
we
cool.
are.
All right.
Yeah.
Hey everybody, thanks for coming tonight. So this is KnoxData, and this is about geospatial computing tonight with Paulo Raposo. It's gonna be awesome. Just quick words. KnoxData, we're a data science group here in Knoxville, and we have a variety of different talks. We've had some machine learning talks this year. We finally get a chance to get back into some spatial computing tonight. But looking for speakers next couple months. So if you know somebody or you yourself are interested in giving a talk, please let me know. We're a part of a bigger ecosystem called KnoxDevs, which is for a group for software developers here in Knoxville, and we have a large Slack group of about 1,100 people here in Knoxville, and so you can get a chance to carry some of the conversations that you have at different meetups offline in between the actual meetup. So anyways, thanks for coming tonight, and without further ado, I'll let Paulo go and get started.
Hi, everybody. So as Alex said, my name is Paulo Raposo, and I'm a pretty young, new assistant professor in geography over here at UT down the road. And really, I'm a cartographer specializing in maps, visualizing spatial relationships, obviously. And that means I also do a lot of what's called GIS, and I know some of you in the audience, that's old hat. Some of you maybe are not so familiar with it. So the first thing we're going to do is do a super cursory overview of what exactly GIS is, and then we'll launch into examples of how to engage with GIS using Python. So GIS is often a very graphical point and click user interface based, graphical user interface based thing, but it is of course also fully automatable and scriptable computing environment. That's what we'll be talking about, is how to manipulate it with Python scripts. Okay. Yay. So folks have probably already seen this from Meetup. Hopefully, if you want to follow along, there's an interactive part of this presentation where we'll be using a wee bit of Python, a wee bit of QGIS, a wee bit of Git, and GitHub. So hopefully you've installed all these things already. But and of course, also one data set that I'd like for folks to go and download. It's on the screen. You download this Lions data set from naturalearth.com. Comes in as a set, runs of it. We'll use that later. Okay, so GIS, Geographic Information Systems, is what this stands for. In a nutshell, it's making measurements from maps on a computer. I am a minority in equating GIS with a very old word called cartometry. No one ever uses anymore. But it's the art and science of measuring things on maps. And of course, on paper, that's tedious as all hell, and on a computer, not so much. Right? So there's a number of benefits and a number of reasons why the world switched to computerizing its geography rather than and modern society, of course, has seen a lot of these benefits. Uber, driving app that got you here today, lots of other things, routing of trucks and logistics, handling natural resources, pretty much anything you can think of that has some kind of spatial aspect can be tracked and managed with a geographic information system, not just because it has a thing in space, right? But also because it has other non-spatial bits of information attached to it. So, car can have its gasoline tank level or something, right? And you can keep track of that all in the context of the where set of things. So, a lot of spatial computing happens these days, especially out of Silicon Valley. That doesn't call itself GIS, but it is. That might be an academic thing for me to say, but when you're doing some form of spatial or place-based calculation, you are engaging in giant umbrella of technologies that is geographic information systems. Okay. So typically, when people think contemporary GISs, they think certain software packages. GIS is more than just a certain software package, right? Some of you, I'm sure, have heard of the Esri ArcMap or ArcGIS. That's like saying Microsoft in this little corner of the market, very super hegemonic, very important commercial vendor of GIS. But there's also been increasingly a very large movement, something I'm very happy about, in open source GIS, in people who are using GIS technologies and software with various kinds of open licenses, right? So at any rate, often GIS sort of in people's minds is the software thing that you open on your desktop. It's the program that you start GIS with QGIS or something like that. In reality, it's more than that. It's the data, it's the algorithms, etc. But often you're faced with a situation that looks something like this. You have a map view. Your data may consist of vector geometry. It may consist of pixels. Those pixels might have come from a satellite image. Things might have been drawn by hand. There's all kinds of ways this data can come in. And usually you have this interface where you have data and you have a pile of tools available. These tools manipulate the data. Right? Tools do some kind of calculation. Like they figure out, well, what's 10 meters away from this point? Or what is this point sitting on top of? It's sitting on top of farmland, right? Something like that. So GIS is this way of asking questions between, especially between, also within, but especially between different kinds of data, right? And asking questions that are usually based on some kind of spatial relationship. So the big paradigm is layers. It's been that way forever. That goes back to the days when we were making maps with Mylar sheets, filing them by tracing light tables and things like that. So digital GIS was designed the same way back when we first conceived it in this layer thing. And you see the same paradigm if you're familiar with, say, Photoshop, right? Or even video editing software. You have this stacked layers thing where what you really care about usually is a two-dimensional representation, and you're using that third dimension just to sandwich a bunch of ideas, right? So with GIS, still to this day, the paradigm is generally layers. Each one of those layers is a theme and a thing. So maybe one layer is roads, and another layer is streams, and another layer is a survey network and a parcel framework, and another one is counties and states and what have you, right? So each one of these things draws whatever it is, put together the sandwich. Now you can start asking questions like which roads pass through which county, right? Roads in one layer, counties in another layer, and because of the way they geometrically intersect or not, right? As an example, you can start putting together some pretty sophisticated logical queries, depending upon wherever your question is, in order to answer something like, how far am I from the hurricane? Or, what is the cost of the hurricane in reaching me in terms of energy, given the fact that there's this mountain range with this slope between? Right? So your questions can really get very complex and hinge off of lots of different data sets. Generally speaking, the two grand families of data are raster and vector. Raster means pixels. Vector means what you think means vectors from Earth. It means little points that are x, y, sometimes x, y, z coordinates in coordinate space, right? And we draw things with points, lines, and polygons. Those things are always made up, elementally, they're always made up of points. So you might have a dot for Knoxville, okay? Or you might have discrete network for Knoxville, which is really chains of little points strung together by short lines called arcs. That's why it's called arc GIS. Right? Or you have a polygon, which is a line that closes. Basically, a line that ends the same place it started. Right? So that's how we model these geometric things on our layers. And generally, we place these vertices, these points, close enough together that you don't really notice that they're short between, and then you can make complex organic looking shapes out of them. Or you have pixels, and then the big thing about pixels is how big, small. So, generally speaking, when we think of something as an object, a car, a city, a country, usually model it with vector data. When we think of something as a continuous field, air temperature, precipitation, political will, things like that, then we can model them as a continuously fluctuating field with little discrete samples, so a raster, right? Those are not hard and fast rules, but usually that's what we end up doing. Whatever it is that we're mapping, if it's object-like, it has discrete boundaries, usually do it with vectors. If it's a continuously spatially fluctuating field, we usually use that. So in this talk today, I'm mostly going to talk about vectors. So vectors are what are often of most interest, really wow, cool, modern, public, attention-grabbing applications. So things like self-driving cars and drones and what have you. These things usually boil down to vector data. That's not absolutely true, but sort of general. So I'm going to talk mostly about vector data and not that much about raster data. Okay. So let's look at a real piece of vector data. Right. What you're looking at is Madagascar, the country off of the coast of Africa. Right. And you can see in the bottom left, I've got, or maybe for viewers online, I should use this pointer thingy. In the bottom left, I've got a polygon, right? A drawn map of Madagascar. And really what this is it's a pile of polygons, right? So each one of these is some, I'm not sure I'm using the right word, but province or region of Madagascar, right? And they're all made up of these tiny little points. And you can see behind this, I've just got a text file open, and it's looking at the bare, naked GeoJSON file that is that Madagascar thing. Okay? So if you're familiar, say, with a Python dictionary, GeoJSON file, or JSON file for that matter, this is just one specialized for spatial things. A JSON file is a lot like a Python dictionary in the sense that you have values, you have keys and values, right? So in the background, you can see, for example, we start the dictionary by opening a bracket, and the key type leads to a value feature collection. The key CRS, which stands for Coordinate Reference System, leads to this another dictionary with another dictionary inside it that explains what coordinate system all these points are in, because there's many different ways of establishing coordinates on Earth, and there's various strengths and weaknesses to the different ways, which is why we're switching back. Okay. And then features opens up into a list where there are a pile of dictionaries again. These terms are not quite correct. This is JSON. But essentially we have these nested directories or dictionaries, if you will, that contain a bunch of data. So you can see in the first couple lines or so, I mean, that's all just one giant wrapped line. But in the first line or so, you see that we've got a bunch of textual things, right? So for example, the name of this place is Betsiboka, right? We have other things attached to it, like its admin code, right? Maybe that means something to the Madagascarian government, right? That's what the admin code of Betsiboka is. There's the postal code, right? And we have various other of these nice little things attached. And then eventually, later off on the screen, we open up to the geometry, which actually draws Betsiboka. That's that monster wall of points. That's just going by point by point by point by point by point by point on all. So in its most naked form, vector GIS data involves a geometric drawing and a bunch of other non-geometric things attached to it. In GIS, we call the non-geometric things attributes, and the rest is geometry. Right? So all these, well, like the text says, right? So in a GIS, when I load this file, this is actually a little screenshot of QGIS on the left. When I load this file in a GIS, all those attributes can be seen in an attribute table, which is what you see on the right. So a nice graphical representation of all these attributes for every province in Madagascar, right? The line I've highlighted here is the one that we're seeing in the background, minus the geometry, because you don't see the geometry table. You see the geometry here, right? So you can see that these numbers all correspond to what we've got up there. So MDG 5869, 7294 is its object ID. It's disme, whatever that is 5869. Okay. So when we compute over these things, this is the data we're manipulating. Right? This is the kind of data, geometry and stuff associated. This, by the way, is the Betsiboka River in Madagascar. It runs like blood red. It's kind of tragic. It's running. It's way out of but it's actually kind of beautiful, despite the fact that it's an ecological disaster. So, yeah. Okay, so GDAL. GDAL stands for the Geospatial Data Abstraction Library. It's a fabulous, wonderful thing, originally put together by a guy named Frank Warmerdam. And you can think of it as a pile of code that constitutes the guts, the real mechanics of the GIS. So it's a pile of code that has formalized and put together and packaged up a bunch of algorithms, a bunch of methods of dealing with data that are very common. That happen. So you don't have to reinvent the wheel, do all your own geometric calculations every time. You borrow somebody else's, namely GDAL, which is free and open source. Or you pay $1 gazillion and you get a commercial GIS, that sort of thing. So GDAL is a library. I believe the original was C, it might be C++, can't remember. And there's Python wrappers that use it, so we can access it with pure Python, right? It's also a set of executables, so it comes with a bunch of little command line programs that are very powerful and very useful. And it also includes, we call it GDAL traditionally, but it's actually two libraries. It's GDAL and OGR. OGR is the vector side of things. GDAL is the raster side of things. We're all called GDAL tradition, right? And these these links, people can follow them later. They're very useful. GDAL. GDAL itself has no GUI. There's nothing visual about this, right? So everything happens on the command line, digital space. Right, so if you want to look at what you've done, then you need some kind of visualizer, say for example, QGIS. Okay. So GDAL is, if you've used ArcGIS, ArcGIS is relatively ensuring that it's constantly showing you what's happening. Not GDAL. GDAL's meant for people who know what they're doing and don't need to be shown every little thing, right? This is a super useful website that comes up in my work a lot, spatialreference.org. remember I said that there are lots of different ways that you can establish locations in the world, lots of coordinate systems, essentially. Everybody's heard of latitude and longitude. Maybe you've heard of eastings and northings. And there's a whole pile of other things. Sometimes they're in feet, sometimes they're in meters. They're only in feet in this country because America. I'm Canadian. but yeah, there, of course, any one real place in the world is going to have different values in a pile of different coordinate systems. So often we need to convert things back and forth. And it's a massive subject in and of itself to explain why we have these coordinate systems. So we won't go into that, but trust me that they're necessary. It's one of the things you have to think about when you're doing spatial calculations, right? You have to think about whether or not all those little points along the line are defined in, say, latitude and longitude degrees, which have nothing to do with the center of the Earth, or eastings and northings, which have everything to do with planar distance and the assumption that the Earth is flat. Right? There are reasons that we go between these two coordinate systems dealing with reality. But you generally need to know why, what coordinate you're working in, and whether or not that allows you to do certain things. So a handy rule of thumb: distance, area, direction, things like that. You can't do that using standard Cartesian geometry with latitude and longitude. You have to do that with spherical trigonometry. But you can do that with eastings and northings, but only over small pieces of the Earth. Because if you start doing it over big pieces of the Earth, the distortion is ridiculous and your numbers are wrong. Okay? So often, when you're running these tools, you need to tell, for example, GDAL tools. You may, or you may not, depending on the project, you need to tell GDAL which coordinate system we're working in, or which coordinate system you want to convert the output to, right? So for example, a lot of modern web mapping uses this custom coordinate system that we only started using about 20 years or so ago called Web Mercator. Now Mercator's centuries old, but Web Mercator is a slight modification to it to make it a little friendlier for computing cycles, right? So if you're going to make tiles for a Google Map-like interface, you might need to change your data into this projection called Web Mercator. Spatialreference.org gives you in multiple different formats. See that little box on the left? It gives you multiple different ways of defining Web Mercator, which you have to use. So back to GDAL here. So GDAL is not part of the standard Python library, but it is of course free and open source, and all you got to do is manually install it, right? So you're familiar, I hope, with PyPy, right? Which is the big central repository, official repository of Python. You're using pip install GDAL from your command line, just like that. You can go ahead and install GDAL as well as all the other packages that it depends on. One of them, for example, is PyDroj, which is a Python version of dealing with math predictions. Right? Or if you use Anaconda, which I hope a bunch of you folks are relatively familiar with, it's a very nice Python machine. If you use Anaconda, you can install GDAL. Somebody put together a GDAL cookbook. Fabulous. It's awesome. Very, very nice. It lays out examples from everything to the very basic, mundane, how to create, down to how to query through all the attributes. So it's a beautiful little resource, especially when you're first learning how to engage with GDAL using Python. Then when you have proper, more serious, more formal questions, there's the proper API, the application programming interface, right? Which is a website that explains to you all the methods and modules and attributes and what have you that are available to you when you're using Paulo. Right? So the cookbook looks like this, right? And click on these various examples and you get these nice little quick snippets show you how to do what's happening here, right? Maybe it's draw a buffer around a line, or maybe it's make a polygon out of a line. Maybe it's take a line and give me all the points, or something, right? And then the API is a big tabular, stodgy, dry reference document where you search for different modules and different methods available. This basically explains everything. Everything you can do and how to do it with GDAL. So it's the big old user manual. I found it helps to understand that there's a hierarchy to the way, I mean, this is programming, there's hierarchies there. Right? There's a hierarchy to the way that OGR, which is the vector part of GDAL, deals with vector geometries, right? So there's a driver, which is part of OGR that knows how to read a certain file type. Because there's lots of file types that can hold vector geometry. There's the data source, which is the actual file on disk. There's the layer, which is the rendered layer, like in a GIS, that file actually produces, has in it. Within the layer, you can have 0 or more features, which are actual things. So, for example, every province of Madagascar is a feature, right? You can have these features. The feature itself has some kind of geometry. In the case of those provinces in Madagascar, they were polygons, say a line that closes on itself, right? And those geometries are always made up at the most basic level of points. So again, in this example, points, right? Or maybe it's just a single point for the city, right? But there's this hierarchy of different strata levels of abstraction to your data. That's how OGR handles things. So that's what you got to sort of keep in mind when you are using OGR to manipulate some kind of certain things happen on certain levels and other things. Right. So for example, if you wanted to ask what is the name of this province, you would need to ask that on the feature level, right? If you wanted to calculate what is the westernmost point in the province, you have to ask that question on the point level, right? So each one of these levels has affordances, if you will, in terms of what you can compute on it. So looking back again at Madagascar here, same slide we saw before, looking at all this data. So that's the data source within which there are features, and those features have a bunch of properties and they have the geometry, which is all the points that make them up. So that's the bottom 3 levels, if you will, of that hierarchy. So let's look at an example of actually running a bit of GDAL on this code, right? Or on this data. So you can see on the right hand side, all I've done is opened up a live Python REPL, or a live interpreter instance of Python. Right? And then line by line, started writing a simple little program. So I've imported OGR, which again is part of GDAL, and they both sit within a meta package called OzGeo. So you import them either from OzGeo import GDAL, or from OzGeo import GDAL, or you can just import OzGeo and GDAL explicitly. Right? And I shouldn't have imported OS because it doesn't matter in this example, so ignore that line. Then, Madagascar GeoJSON is a string to the file that I've got saved. Right. And if you're a Mac or a Linux user, that'll make sense to you. If you're a Windows user, sorry, there's no file. Okay. So that's where my Madagascar.geojson is sitting. And back to this GDAL hierarchy business, I need a driver. I need to tell GDAL how to read this file. It's the same thing as when you need a driver to use a printer, right? The driver is a piece of software that teaches your computer how to interact with this data, right? So I need a driver to deal with GeoJSON files, right? So I get myself a driver, which is something I can do from OGR for GeoJSON. And I create a data source by using that driver to open my Madagascar.geojson file, right? And then I need to go down one more level in the GDAL abstraction and get the layer out of that thing. So data source.getLayer, right? And there's lots of examples of that in the Python cookbook. And of course, it's detailed ad nauseum in the API, right? But that's a very typical basic suite of how you open a vector GIS file of a GR. At this point, I now have access to all that data and I can do stuff with it. Right? So quite simply, all I'm doing is going to loop through all the features here, right, with a simple for loop. Right? For feature in layer, because layer is going to have a bunch of features, and these are all the features. Right? For feature in layer, I store its name by saying feature get field name, right? And that's because it's got a field called name. There it is. And in this case, it's Betsiboka, right? For feature, give me the name. I also get the area of square kilometers because that's been pre-calculated in this case. And I put together a simple little string, right? Where I have the program report back to me that the province of Betsiboka has an area misspelled of 30 grand. So this is how I can access that data, right? And having accessed that data, I can make computation on it, of course, right? So I could calculate, say, the average area of the states in Madagascar by taking all those numbers and dividing by the size of the lake, right? So this is basic reading. And you can also write to and create brand new files with GDAL. GDAL handles lots and lots and lots of formats. One of the nice things about GDAL is it's kind of like a GIS Swiss Army knife in that it takes in and puts out lots of different formats with some limitations. Usually those limitations are legal. So sometimes it can read a proprietary format but not write. Right, so you can read, for example, an Esri file geodatabase, which is a proprietary Esri format. You can read that with GDAL, but you can't write it because they're forbidden for legal reasons to be able to create one. So you can read it, do your work, and then save it to some other thing. That's what you can do. So, again, GDAL comes with these great command line tools, which are, depending upon how you've installed GDAL and depending upon whatever it is you're working on, they're compiled for your native OS. So in my case, Linux, in this example on the screen, this was done on a Windows machine, so they're .exe files, right? So these are programs that you can run, right? And you can run them from the command line. These are programs that don't have GUIs. No window pops up for you to see anything. They're just ready to do stuff based on what you tell them on the command line, right? So, for example, here, I've asked GDAL warp to show me its help message, right? And it just plops out all this stuff, right? Which is a bunch of things that I could ask it to do on the command. I know some of you are probably totally old hat, and some of you are totally new to access a program. But the same way that you say, use an ArcGIS tool and you say, here's my input file, and I want my output file to be named this, and I want you to use this tolerance, and I want you to use that. All those things are arguments, and you can give a program arguments when you run it from a command. You haven't done that before, right? And that's how we use these programs, these GDAL executables. Is we use them on the command line, we hand them whatever arguments are necessary, it does its job, shows us nothing, does its job, saves it to disk, and we're done. So this, for example, is saying that there's only 2 required arguments. You need to tell GDAL warp what file to start with, and you need to tell it what file to write to, input, output, right? But in the meantime, there's a zillion other things you could define. Change the coordinate system, you could change the file type, change the resolution, you could change all kinds of things, right? And all those different options are things that you have to go look up in the GDAL API online. Choose the options that work for you, right? So here, for example, let's use GDAL warp, that same program, right? So GDAL, remember, is rasters. Okay? Rasters are these flat sheets of pixels that sit on the Earth, right? Sometimes those flat sheets of pixels are in fun shapes because the Earth is round, right? So if those flat sheets of rasters are covering a big enough area, you might have to deal with the fact that they need to warp differently around the surface of the Earth. But GDAL warp is essentially a program that's all about performing the necessary complicated geometric warping so that that thing is in the right place on Earth, basically. So we call this reprojection, cartography land, right? Or transformation more generally, but warping is what's happening geometrically. You're taking a rubber sheet and you're changing it in whatever shape you need. So in this case, for example, I've said, hey, GDAL warp, I want you to write the output as a GeoTIFF, which is one of the more flexible and powerful raster pixel formats. It's open source as well, not proprietary. I want you to write the output to a certain coordinate system, EPSG 3742. EPSG is the European Petroleum Survey Group, and they ended up becoming a sort of global standard because they defined a bunch of coordinate systems with code numbers, and everybody else started using it. So it's a handy way, it's a fast way to say Universal Transverse Mercator 12 North, in this case, right? Or a different EPSG code would be Web Mercator, or a different EPSG code would be Tennessee State Plain, right? These are all things you look up. So of course, you don't memorize that stuff, right? And then I give it an input image, big long file path here, right, of an IMG file, right? And I write the output after having reprojected it, after having warped it. I write the output to this TIFF file, right? And I have to have told it explicitly that I want the format to be a TIFF because the .tif doesn't actually indicate file type, at least not on Unix machines. It does on Windows machines, sort of. But I have to explicitly throw in this optional argument and then call it a TIFF. And then it screams along, and in a matter of split seconds, it's done. And we can visualize what it has done here. The next slide. So this is a DEM, a digital elevation model, right? So that means a bunch of pixels where each pixel is simply recording how high it is above sea level. So that's a nice way of representing topography. Very, very standard way in GIS of representing mountains and hills, watersheds, having a digital elevation model. And you can see on the left, that's the digital elevation model of this river drainage basin, right? Before I changed its coordinates. And on the right, that's it after having work. So that program performed some complex math and geometry to change the coordinate system of my data. But maybe I needed to do that because direction is preserved here but not area, to calculate area. Different ways we can map the world either screw up the shapes or they screw up the areas. Or we have to choose between the two. There's no possible perfect compromise between the two. All right. So, in addition to the nice executables on the command line, which, by the way, you can always call from a Python script by using the sub-process module. Python's got this nice little standard library. You just import sub-process. The sub-process allows you to ask the OS on whatever computer you're on. It allows you to ask the OS to do something parallel to the Python code, to do something subordinate to the Python code. So it's like opening up a terminal, asking the OS to do something, and waiting until that terminal is run. Right, so you can run anything. You can open Microsoft Word from a Python code by using this process. Right. So you can always use those executables that come with GDAL. But another way is to directly engage with the library through that C wrapper business. So you can actually write Python code. This stuff is not Python. It's Bash or PowerShell or CMD or whatever situation you're in. But now we're going to talk about using it with Python. Right. So at this point, if you want to follow along with me, if you have Anaconda installed, one of the nice things about Anaconda is it helps you manage environments, which is to say isolated little installations of Python, where you can have certain other packages installed. The reason why you want to do that is because sometimes in your life you want to make accounting calculations, and other times in your life you want to make spatial calculations. And the libraries you need to do this conflict with the libraries you need to do this. So it's kind of like having baby little Python computers in your one computer, keeping them isolated so that they don't interfere with each other. Call that an environment. Right. So Conda allows you to create multiple environments, and in each one of those environments, set the thing up so that it's ready to do whatever it is you want to do by installing other packages. For example, GDAL. Right? So if you throw open a terminal on your machine, right, in Windows you can hit Windows R, CMD, enter. Or if you're in Mac, I don't even know how to get a terminal in Mac. Or if you're in Linux and you don't know how to open a terminal, then why are you so if you open up a terminal, go ahead and make yourself a directory somewhere that you have write access. Right? So perform this front line here. Make dir. You can call it whatever you like as long as you remember that. Go ahead and call it KnoxData GDAL demo. Right? Once you've done that, you cd change directory into your new directory, KnoxData. So maybe what I should do is do this live with you. So I can make a directory called KnoxData demo. I can change into that directory. You can see my prompt has changed to indicate that I'm now inside that directory. Right? Then I I'm going to use Git, which is this software that allows you to keep multiple versions of software on your machine. It also dovetails with GitHub, which you've probably heard of, which is where a lot of open source code lives for people to download. So I'm going to clone a repo, which is to say I'm going to go to the collection of code online, and I'm going to copy it to my local machine. Right? So I'm going to git clone, and then I need the address of this thing. GitHub.com, crazy guy who wrote it, and flow maps. Hit enter. Computer goes online, finds the code, downloads it, loads it into my file. Now, if I look in my file, my folder, you'll see I have a new directory that I can switch into called flow maps that is full of stuff, including a Python file called interpolatedflowmaps.py. So if you've done that much, what you've done is you've gone to my repo online and copied it all down to your machine, which you're allowed to do because the repo is public. Open source software. Okay. So we've already moved into that repo, into flow maps. Here on, where's my little terminal? There it is. So we've already moved into that repo. But another thing you want to do, wait a minute, sorry, I'm ahead of myself. We need to do this. We need to do this first. So if you've got Anaconda installed, type the word conda, press enter. And if you get something like this, that means conda is installed. If you don't get that, you haven't installed conda. Most likely. But conda creates an environment by the name of flow demo. And in that environment, please install version 3 of Python and make sure that you get GDAL, SciPy, Shapely, and PyProj when you build the environment. At line it says, make me a brand new baby installation of Python, Python 3, make sure that it has these packages. Now it goes online and it finds all that stuff. And it's going to tell me, sure, I can give you all those packages. I also need to give you a pile of other packages that go along with it. Right? So as soon as it finds that, here we go. Now it's telling me I should update conda, whatever. There we go. And it says, actually, I need to install all of these in order to fulfill your request. And then I say, yeah, that's fine. Go ahead. Okay. And it starts downloading lots of different packages that will enable 4 packages that I have to use. And that'll take. Is anybody having trouble following along? Can I help with any terminal issues while this is loading? Oh yeah, the AT&T network, and I don't know the password though.
Yeah,
oh, the password is this long number. Yeah.
Might take a long time.
This might take a long time.
And
then there's everyone else. Yeah, taking up the title. That's true.
That's right.
whatever that is. It's a big library.
Yeah,
MKL.
yeah.
If that speeds up, cool. If not, then this is going to take too long.
Yeah.
Yeah.
Yeah. Our list here is not.
Okay. I'm going to kill that one. But you guys can get copies of the slides and probably do this at home where your internet is faster and whatnot. But I already have an environment that works. So I'm going to activate my environment like so. So really what I was doing was creating an environment that would have been called flow demo. And instead now I'm just using one that I've already set up on my machine called GDAL. It has all the necessary packages. And by source activate geo, except if you were on Windows, it would only be activate geo. By saying that, I'm basically telling this terminal window, hey, when I ask for Python, I'm asking for that certain installation that I called geo. So Python will be able to find the certain libraries that I want it to find rather than rely on the default installation on the computer. All right. So one of the things I can do, like the slide says here, is I can look at the help page that I wrote for this script, right, which essentially tells you how to use the script. Okay, so in order to do that, I say Python, I want you to run interpolated flow maps and give me a tell message. And Python's going to try to run it, and it will be able to because I have all the necessary packages. But any moment now, there we go, bang, I get this big long gobbledygook, which is essentially a set of instructions like we saw before with the GDAL executables, right? These are a set of arguments that I can give the script, and it will do work with those arguments, depending on what I ask it. So it wants an input CSV file that specifies a bunch of routes. This, by the way, is a script that I wrote and am writing, still developing it, that makes flow maps, because flow maps are really hard to make by hand, right? It makes flow maps, and you need to tell it, well, I want to start here and I want to go here and I want 700 units to flow, right? Maybe that's people, maybe it's sheep, maybe it's dollars, right? And I want to start here and I want to go there and I want this many, blah, blah, blah. So then it's going to draw that flow network, right? So the two things it needs to have are, give me your routes, which have to be in a CSV file, and where do you want me to write the output? Right? These are the two things I need to tell my Python script for it to do its job. And it's going to use GDAL to do its job. Right? And then there's other things I can tell it. I can change the way the lines are drawn. I can change how many points along the lines are drawn. I can bend the lines more or less. I can bend them to the left or I can bend them to the right. These are all things that I've programmed into the script to be able to allow the user to choose, right? So these are all optional arguments with little dashes, right? Things like that. So what we're going to do is just run the default example. So you'll notice that in this directory, ls is short for list. So show me the files in the directory, right? And can see the same thing. There we go. More comfortable graphical environment. Inside home folder, I have made KnoxData GDAL demo, and there's flow maps. And there are the three files sitting in it. And you can see interpolated flow maps, py, readme, and test data. So this is the Python program This is some gobbledygook that tells you how it works. And this is some test data that I've packaged with the script so that people can easily give it a spin, right? And so that they know how to form their own data when they want to make a flow map. So that test data looks like this as soon as this opens. It's going to ask me about formats because it's a CSV and the defaults are good. A little laptop. You can do it. There we go. So I have a CSV where I've said, give me a starting place. That's a beautiful city in Azores, Portugal. Visit when you can. Its latitude, its longitude. Give me an ending place, its latitude, its longitude, and give me some flow magnitude. So these are the necessary inputs for my little tool, right? And I'm going to go ahead now on the command line and ask it to do its job, which is to say, use the test data CSV and write out something called outfile.shp shapefile. Now, my script is going to run in the background. And bam, it's over. So that's just like running a tool in ArcGIS, but nothing pops up to show you what happened. It just got written to disk. Well, let's go ahead and see what happened. You'll notice that now there's outfile, SHP, PRJ, DBF, etc. in here, right? There's a bunch of things that I can now look at using a GIS, which I'll crack. And that's what it looks like on the terminal, right? And while QGIS is opening in the background, we can have a look at what this thing looks like. Maybe I should have brought a faster laptop. Well, I'll show it to you on my live disk in a moment as soon as QGIS opens. But you can see on the slides here, those green lines are what my script did using pure Python and GDAL. Right? And then the background shoreline, that's the data set I asked you to download just so that this actually looks like something instead of a bunch of quick lines. Right? So that is the map, if you will, that we've produced, and with a little bit more tweaking and care, you can make that look considerably better. That's a little bit more point click map design business that needs to happen before that starts looking interesting. Right, so here's QGIS. This finally, oh, come on. Here's the script. So this is what we downloaded from Git. This is a whole pile of Python that does that line drawing. Blah, 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 blah. Right. So of course you can read through it. This is a relatively, I mean, there's far more complicated out there, but this is a relatively involved, complicated, I don't know, call it professional level script, right? Sometimes your scripts will be far shorter. They'll be 10 lines long, right? This is more like 500. But this is pure Python, and it uses PyProj and GDAL and lots of other things to do its work. Here's QGIS. Here are my files, and I can drag this right in. And there you go. You see my lines that were just computed in the background. And I'm going to go ahead and go get myself some GIS data as well, which I have preloaded so that we can see what that looks like in the background as well. Where are we? Things. I think we're getting on to it, so I don't want to keep you guys long. I think we should be here. But yeah, so I mean the slides are on the meetup page. You can follow the link and get the slides. Feel free to walk this through yourself. I hope it wasn't too bewildering or too simple. I figure for some of you this is totally new. For some of you, but just a taste of what's possible with totally free open source. So thanks for coming.
Thank you.
Sure.
What else was I think it was something for I didn't know about the cookbook. Your open source tool. Absolutely cool. Yeah, so I that's my response. But it's one of those things like I know I have no use for it right now. But like
One day.
But one day, wouldn't even I
Well,
would need that.
a friend, you know him, Ted.
Oh, yeah.
A friend asked me, Paulo, do you know of any methods to make flow map? And I was like, no, I don't. I'll write one. Literally. Because it's like, yeah, there aren't any, right? Or at least not really. There's a handful, but kind of funky. And so I decided to write one. We gave it free to the world. Yeah.
So the formats, you showed a shapefile, but you output to other.
Cursor. Sorry. Here we go. Viable options are shapefile, KML, GML, GMT, or GeoJSON. So those are all files that GDAL can write to. GDAL can write to lots of other things, but I bothered to set it up for these. And KML is what Google Earth, right, normally uses.
Question for you. So you know handles, geo. Have you played with that?
Never touched it. I know it exists, but I've never used it.
Yeah, I use it a little bit briefly.
And it's must be for map drawing, right? Because Pandas is all about.
Yeah, I mean I guess it's really about having feature set. It's focused on the features. It's the fact that your geometry is basically just a column. Everything else, the data that you're basically, it's like having a tabular data set, and then you have a column for all your geometry that corresponds to each thing. That's kind of mindset. So obviously, it uses a lot of GDAL. Obviously,
I would think. Actually, a lot of the guts of QGIS.
but a lot of it has a lot of the same syntax as Pandas. So if you're used to like combining different data sets, and let's say you have a geospatial component of that, and you want to be able to mix and match. I'm sure you can do it GDAL and stuff. GeoPandas basically just makes it just like
makes it easy to do
like
with
you will with pandas.
SQL or something.
It essentially kind of forces you to use simple features or whatever, well-run text, and basically break up the geometries into a column. Add on to it. But I've only played around with it. I haven't really used it.
Yeah, I've never used it either. There's a lot of things out there for drawing maps. Like, I mean, you could even get Matplotlib to draw maps. Not well. Like, you can get it to draw basic polygons, but not great cartography. But all you need is polygon to find. So there's if you ask me, the finest and most powerful and most interesting of all the packages is GDAL, because it's been around forever. It's very powerful, and a lot of the other packages are actually just using it in the background. So it's probably the most valuable one to learn. But yeah, certainly there's other things. There's Shapely. Shapely is all two-dimensional geometry stuff, and it's kind of meant for maps.
So this is another side comment that you kept bringing up on GIS. So one of the great features about QGIS is the plugins, because it comes stocked with a bunch of goodies, but it also has plugins, and people contribute to plugins so that people add useful utilities all the time. And almost all of those plugins are written in Python. And they even have, you can even draw using IQT to draw the QGIS lines and polygons and stuff like that too. Yeah, you could spend all night just doing a tour of all the stuff that's on GIS, but
yeah, that's true.
Yeah, there's the plugins. It's going to take a second on the Wi-Fi to get everything, but oh yeah, you got that one.
Where is the? Guys, they don't have any open layers. I think it was.
First, yeah, it's all small.
There it is.
Oh, really?
How cool that stands. There's further tiled.
Yeah. I'm installing a plugin to QGIS right now that basically can automatically suck in Google Maps and Bing Maps and Stamen Maps and a handful of others. Right. So now, where do I get it? So here, there it is. Yep, there we go. Okay. So give me a Bing aerial. Nope, not gonna let me. Oh well. Oh, there we go.
Now you just have to move the layer down. Yeah.
There we go. There we go.
Easy peasy.
And then I can start doing some fun stuff by going into the properties of this. And I can say, no, I don't want a simple line. I actually want that to be an arrow. And I want it to have a single head type of type plane. And the arrow width is going to be a variable based on the flow magnitude of the line. So inside fields and values, I can say flow mag. Make this window bigger. There we go. Flow mag, and I also remember that number needs to be seriously down. So you can start seeing I've started to apply these things to the arrow, and I can do fields and values, flow mag. And it's fine. And the head, the thickness should also be that. So Okay, and I do want curved arrows, and I don't want to repeat them on segments. There we go.
Yeah. Wow.
Right?
Did anyone time that?
Not professional right here.
So
It's almost like he's done this a lot of times.
right. And then I can do things like show labels based on the field. Which field do I? Oops. Show them based on destination. Apply. And I'm going to go ahead and make that text something that's a little easier to see right now over this imagery. There they are, right? And I can do much fancier things than say that. So for example, instead of using that, I can say fields and destinations org. Concatenate that with the string to an emoji. Test. And
Oh, man.
so you can see it's starting to get more and more refined, right? So these are all little touches that you can do with GIS, and this is all automated. I mean, like really nice cartography. Then you go in and humanly touch up things. But this is just quick and dirty. It's starting to throw things together.
Can you hard code some of that stuff in like a script?
Absolutely, you can hard code all of this.
Can you?
QGIS is entirely scriptable in Python.
Yeah, I mean, is there a way to look at the script behind what you've done here so you can copy it?
Some of the tools will give you the GDAL command line arguments that are necessary to run them. What I'm doing right now, I don't think you can get verbatim. Here's the Python version of what I just clicked on.
Yeah.
But I know you can get that at least with a lot of the tools that are based on GDAL. However, there is a scripting API for QGIS, right? And also a bunch of help tutorials and guidelines. So I mean, that's a way to get used to that. ArcGIS also has the same capabilities.
Pay for it.
Yeah, and you have to pay for it. I'm a huge lover of QGIS. In my humble opinion, ArcGIS's Python scripting is way more elegant. But QGIS is possible too. So, yeah. Here I can say doing some more concatenations, just getting fancier and fancier, and full mag plus did I do that correctly? Expression is invalid. What did I do wrong? What did I do wrong? I did something wrong. What did I do wrong? Is it because that doesn't come back as a string? That might be why. Versions to string. Yeah, that's probably why. There we go. Here we go.
All right.
Could I ask a question? So I'm an editor. I use R stats.
Awesome.
Use all the packages that Robert Newman's has developed. The one thing that I've consistently had issues with is generating new vector data de novo. So I often work with, say, like UN country level point estimates. And I wanted to interact with a raster.
Huh?
And my workflows didn't really hack together. I often take a different shape file and then I prep the country names, and then I assign a new field, and then I export it to a raster. But do you know if there's a better way where when you're working with these large-scale data sets where the index of a state or a country and you want to transform into a polygon and then export it to a raster, other than having to hitch a ride into an existing shape?
So the answer is there's always a way,
Okay.
and it depends upon what your starting data is. So if all you had was like Kansas.
Yeah, usually. That's
Okay,
the
so if that's all you have,
Yeah.
then you do need at some level to start with some other geometric data.
Okay.
Right? But you could, for example, let's say you wanted to reduce Kansas to a point.
Yeah.
Right? Then you could take the polygon of Kansas.
Yeah.
And you could use GDAL in this example. There's lots of it. You could use GDAL, stream through all of those vertices, find the average X value and the average Y value. Right? Spit out that point. That's the geometric centroid. Right? I'm not sure if that's the centroid.
There's even centroid calculations.
Yeah.
And yeah, a lot of GIS actually do have existing tools where
Processing, I guess.
we pull in some data. Okay, so here we go. Right, so here's country polygons, and one of the things, for example, that's pretty simple is it here?
Yeah.
You see it? Create. Where am I? Oh, I don't see it. That's the lines. Polygoncentrics. Thank you. There we go. So now, whoops, here's a tool where I can say, yeah, create temporary layer. That's fine. Okay, go, run. There we go. So that has taken every little polygon and gone ahead and found the point that sits its geometric center. Turn this off a little faster. Right. So these are the kinds of stock and trade calculations that you can do with GIS. Right. And that polygon, these countries, this was free data downloaded from Natural Earth, the same place in the tutorial, which is a fabulous set of basic world vector data put together by two very excellent cartographers I know personally. So, but yeah, so I mean, there's that sort of thing. So now that point, you'll see each one of these points, everything keeps showing up on my second screen. Each one of these points you see is associated with the polygon it was made from. So there's Armenia, right? And so it sucked up all the data that the polygon had, right? Including its formal English name.
That was the other thing.
Oh,
Yeah, okay, this is,
that's worth its weight in gold.
yeah, like, I don't know what I'm gonna do with this, but I know I can do something cool.
But then you go say thank you, Tom Pascal. Yeah, I mean, I hope that's useful and, you know, gives you a peek into an enormous world of possibilities. I've only pointed vaguely at a concept. So.